Most people who start learning electronics will never be able to learn and use transistors well until the end of their lives. Why is learning transistors so difficult? Maybe lack of practical information and content is the main reason. Transistors are used for switching and amplification. This is the most basic definition of transistors. We have already heard a lot, but this is so ambiguous. What does it mean? What exactly does a transistor do in a circuit? I know there are a lot of videos about transistors, but this video will be different. In this video, I'm going to talk about transistors in practice, not their inner structure or chemistry or other trite stuff. In this video, I will answer this crucial question: where in a circuit should I put a transistor? In this video, I will bring you 7 examples and practical experiments, not just theory, that show you different transistor rules in circuits. Please stay with me until the end of this video. These lovely components are called transistors. They are available in various types, shapes, and characteristics. Transistors are so important to learn and mysterious. Transistors have 3 main categories of application: using the transistor as a switch, using the transistor as a sensor, and using the transistor as an amplifier. But before going to the first application, I have to mention that transistors have many parameters. I made this video assuming that you are familiar with these basic parameters. So let's go to the first application. I think the first application I'm going to mention is so predictable. Application number 1, using a transistor as a switch. Using a transistor as a switch is the most common, simple, and cliched application of transistors. By applying voltage more than 0.7 volt to base emitter junction on this diagram, or voltage more than threshold voltage to gate source on this diagram, the transistor will allow current to pass through itself and eventually it will turn on the load. The load can be any DC component, a DC motor, a relay, GLCD backlight, or even a larger transistor. This DC motor draws maximum 500 milliamp at 12 volt, and this BD139 BJT transistor can withstand maximum 80 volt on its collector emitter junction and handle 1 ampere of collector current. So this transistor seems to be suitable for switching this DC motor on and off. Since BD139 is an NPN type BJT, it is better to use it to switch ground voltage. When I press this tactile button, 3 volt will be applied to base terminal of this transistor and it will turn this transistor on, and eventually this motor will be turned on. Look here and pay attention to these ampere meters. This ampere meter is this one, and this ampere meter is showing all current flowing to collector of this transistor. Look here, this is 8 milliamp and this is about 30 milliamp. Let me put away this tactile switch this way. I'm using this wire to connect both terminals of this tactile switch and put it away. Look here, this is minimum collector current drawn by this motor, and this is about. By looking at ampere meters, it becomes clear that the current flowing to base terminal is very low, constant, and it's about 8 milliamps, but the collector current can be variable from 13 milliamps to 400 milliamps because of the DC gain or HFE of BJT transistors. Using transistors as a switch makes us able to control state of a high-powered DC load through commands from low-power sources like microcontrollers. In addition, transistors makes us able to automate some tasks. I mean making some tasks controllable through software. I wanted to give you more examples of the use of the transistors as a switch, but I think using transistors as a switch is getting boring. There are a lot of online content about this subject and there is no need to repeat them in this video. So I'm gonna add some salt and spices to this topic to make it more delicious. Application number 2, using the transistor as the main switch. Using transistors to switch a DC part of the circuit like a DC motor, LCD backlight, etc. is relatively straightforward, but you can use a transistor to switch the whole circuit. You may wonder why switching the whole circuit using a transistor is so important. Let's see some examples. This is a toy ball. If you hit this ball somewhere, it will start to work and make the RGB LED blink like this. After a while, it will turn off itself automatically. There is a knock sensor inside the ball, something like this. The mechanism of the knock sensor is very simple. There is a spring and a pin inside the spring like this. When the ball hits somewhere, this spring will bend and touch the pin for a moment, and this is enough to turn a transistor and eventually hold the circuit on. This toy car is another example. There is a tactile switch inside the car instead of knock sensor. The switch is placed under front wheels of the car. When you press the car, it starts to make sounds and turn on two LEDs here and turn off itself after a certain period of time. This is basic diagram of using transistor as a main switch. Here I have used a P-channel MOSFET to switch source voltage. You may wonder why I didn't use BJT and I used MOSFET. Actually, switching whole circuit can be done using either BJTs or MOSFETs. Here I prefer to bring example in which MOSFET is utilized to do this task. You may ask why I use the P-channel MOSFET. Good question. In one of my previous videos, I said that P-channel MOSFETs are mostly used to switch positive side of power supply, meaning source voltage, and N-channel MOSFETs are mostly used to switch negative side of power supply, meaning ground voltage. In this case, where we are going to switch whole circuit, it is better to use a P-channel MOSFET to switch source voltage to reduce resistance in ground path and make the circuit more reliable and more stable. Putting a transistor, actually a resistor, in ground path is a big mistake. This is the main reason why I used a P-channel to switch source voltage. Let's analyze the mechanism used in this diagram. If you connect these 2 points together using a knock sensor or a simple tactile switch, it will connect gate terminal of the MOSFET to ground, and the MOSFET will turn on and connect source voltage to main circuit. Since it's a P channel, it should turn on when the voltage on gate source is negative or voltage on source gate is positive and is more than a specific value. First thing the main circuit is gonna do is to sync gate terminal of the MOSFET through this green wire to keep the transistor on. The main circuit will run its program, and after finishing its program, it will source the gate terminal of the MOSFET through this green wire, and it will turn off the MOSFET and eventually whole circuit. Also, we can add some slight changes to this diagram to make this button readable to main circuit while it is running. Using a transistor as a main switch makes it possible to turn on and off the device using same digital button, something like this LCR meter. Also, by using this technique, you will be able to implement auto turn-off capability in your designs. In addition, using a transistor as a main switch makes it possible to turn off the device completely for a long period of time in order to take its power consumption down to almost zero and eventually increase battery life. This technique is widely used in IR and RF remote controllers. Next item in the list is my favorite, application number 3, using transistors as a sensor. All electronic components are sensitive to heat. A transistor is not an exception. Almost every parameter of a transistor will be affected by changing its temperature, but I'm not going to explain how to use a transistor as a temperature sensor. It is not very practical. But using a transistor as a touch sensor does not seem entirely pointless. This is most basic diagram of a touch sensor using MOSFET. All you need to do is to charge this capacitor inside the MOSFET to a specific voltage. Since capacity of this capacitor is extremely low, when you put your finger on these electrodes, it can be charged through your skin very fast. Also, you need another resistor to discharge the capacitor when you put your finger away. Value of this resistor should be very high compared to skin resistance, for example 10 mega ohms. So when finger and resistance of this resistor work together, the voltage on gate terminal will get a suitable value and turn the transistor on completely. This touch sensor is working very well. You can use a spiral form touchpad instead of this header to improve touch sensor reliability. Also, we can implement other sensors using transistors, for example, pressure sensor, humidity sensor, light sensor, and so on. But I will ignore them in this video because there is nothing new in them. We usually think that transistors are used for amplification, and this idea makes some of good uses of transistors hidden from our eyes. Application number 4, using transistors to restrict current. In the first application, we discussed using transistor as a switch which blocks current completely or allow current to flow freely. In some cases, we need to limit the current to a certain value. Using transistors is essential in such cases. You may ask why we don't use resistors to restrict current. Good question. Actually, we do in some cases. For example, we always put a resistor in series with an LED to restrict its current, but in some other cases we can't. This box indicates the current limiter circuit. Its job is to limit amount of current flowing through it. This is most simple current limiter circuit ever using a single resistor. By using this method, the current will always be limited, and also voltage on point A will be affected by the current amount flowing through the resistor all the time. Also, we have no control on the current limit. By assuming a constant value for this resistor, the amount of current will depend on the voltage difference across the resistor. In some cases, we need to limit the current only when it reaches to a specific value to have a constant current. Let me clarify the problem. If the load on output draws current less than the threshold value, say 1 ampere, the voltage on output will remain constant and equal to 12 volts. But if the load on output tries to draw current more than 1 ampere, the threshold value, the voltage on output will decrease to keep the current on output constant and equal to 1 ampere. This behavior is useful in battery charger circuits and lab bench power supplies. To charge a battery, we have to limit the charge current for safety and other purposes, and in that case, a current limiter will help us.
This is most basic current limiter circuit using transistors. Here there are two transistors. This one is main transistor and delivering almost all the current to the load on output. And this one is used to control the first transistor. Also there are two resistors here. This one is for switching on the main transistor and this one is sense resistor, also called a shunt resistor, and its main job is to sense the current amount delivered to the load on output. We have to select a low value for this resistor and relatively high value for this one. Current threshold is set by using this resistor. Using different values will result in different current limits. For example, a 0.6 ohm sense resistor will result in 1 ampere current limit, and a 0.4 ohm will limit the output current to 1.5 ampere. Let's suppose that we have selected 0.2 ohm value for this sense resistor. If the current on output is below 3 ampere, then the voltage across the sense resistor is below 0.6 volt. Since this sense resistor is parallel with base emitter junction of this transistor will be off and this transistor will be completely on. If the impedance of the load on output gets decreased, then it will draw more current. If the load tries to draw more than 3 ampere, the voltage across the sense resistor will become more than 0.6 volt. Eventually, it will turn on this transistor, and then this transistor will take down the voltage on base terminal of this transistor, and finally, this transistor, which is tending to off state, will increase resistance on its collector emitter junction. So, the voltage on output will be decreased to keep delivered current to output constant.
If the load needs more current, this circuit will try to reduce output voltage to control the current. So, this process will result in a balance which will lead to a constant current equal to current threshold. Unlike using transistors as switch, current limiters are smart switches which can automatically switch a portion of the input voltage. Using transistors will get more interesting if you use them to amplify voltage. Application number 5. Using transistors to amplify voltage. One of the most beautiful and interesting applications of transistors is to use them to amplify voltage signals. This application of transistors is practical in active region of operation of BJT transistors. You may ask, what is active region of operation? Good question. There is a misunderstanding about BJT transistors among beginners. They think there is a threshold voltage on base terminal of BJT transistors, say 0.7 volt, which applying more than that will turn the transistor on, and applying less than that will turn the transistor off. This is somehow true, but I have to ask an important question. What about 0.69 volt, which is less than 0.7 volt?
What I want to say has no scientific basis, but it can help you have better understanding of transistor behavior. Actually, transistors have two threshold values instead of one, and they work like this. If base emitter voltage is under first threshold, the transistor is completely off, almost. And if the base emitter voltage is more than second threshold, then the transistor is completely on. But if the base emitter voltage is between these two thresholds, the transistor is partially on. The transistor shows its voltage amplification behavior when it is partially on. I'm gonna generate a very tiny signal using my signal generator and apply it to base terminal of this transistor, then probe this point using my oscilloscope to see the voltage amplification behavior of transistors. This blue sinusoidal signal is the input signal. The amplitude of this sinusoidal signal is something around 100 millivolt, which is very low. But the amplitude of the amplified signal, I mean this yellow signal, is something around 12 volt, which is 120 times more than the input.
Let's add some excitement to the topic. This is a typical RF remote controller. When you press a button on remote controller, it emits radio frequency waves with a specific modulation at 433 MHz. In this video, I don't intend to explain RF remote controllers and their protocol or modulation. The importance of using a transistor to amplify its signal is important though. This is a simple wire. When a radio frequency wave hits this wire, it absorbs a portion of radio frequency wave and it changes electric charge on the wire.
This transistor is biased using this potentiometer. Look here, any changes in electric charge on this wire will affect the capacitor, and somehow it will pass the capacitor and affect the voltage on base terminal of this transistor. These tiny changes on base terminal will cause larger changes on collector pin voltage, I mean point A. Actually, it will be amplified. I'm going to set up this circuit and probe point A using my oscilloscope. When I press a button, you can see the waveform transmitted by the remote controller. I have to put the remote controller beside the wire to better receive the signal. Look here, this is digital form of modulated signal, and this is analog wave transmitted by the transmitter. The frequency of this signal is equal to 433 MHz.
You may ask many questions about this circuit and remote controllers. Actually, these are not subject of this video, and I will talk about them separately in one of my next videos. Also, this receiver is not a good receiver. A good receiver needs sophisticated filters and complicated amplifiers. Only the voltage amplification behavior of transistors was the point in previous experiment. So now we are moving to the next application, application number 6, using transistors to amplify current. A current amplifier increases the strength of a signal. A strong voltage signal can deliver a lot of current without a voltage drop. I think it will become more clear if I give you an example.
This is the example, a voltage source which can vary from ground to VCC, say 12 volt for example. I'm gonna connect the middle terminal to oscilloscope and test it. When I rotate the handle, voltage on middle terminal changes. But this variable voltage is so weak and useless because it can't deliver current. For example, if I connect the DC motor to this point, I mean point A and ground, hoping to control its speed, voltage on point A will drop to 0 and can't run the motor. For example, this motor. This is what I call a weak signal or weak voltage. There is no problem with voltage range. It is between 0 and 12 volt.
In this circuit, we have a weak voltage coming from middle terminal of the potentiometer, which can vary from ground to source voltage, but it can't deliver enough current. Here is where the transistor comes into play like a superhero to make the voltage strong.
The transistor is used like this. This configuration of transistor is called common collector or emitter follower. The voltage here on point B is almost equal to voltage on point A, but it is much stronger. Let me connect the DC motor to point B and see what happens. I have explained this circuit in detail in one of my previous videos. There is a link to that video in description.
This configuration of a transistor is extremely practical. Everywhere you find a weak voltage, you can use this configuration to make it strong. For example, you can use this configuration to make a Zener diode output voltage strong enough to drive the desired circuit. Or you can use this configuration to make a sound signal strong enough to energize a speaker. Or even you can use this configuration to increase output power of a tiny and simple regulator up to several amperes and so on. You just need to connect the base terminal to the weak signal, collector terminal to a high and strong input voltage, then your strong output signal will be ready at the emitter terminal. Last but not least application of transistor is to use them in audio amplifiers. Application number 7, using transistors to amplify audio signals. The audio amplifier is nothing but a voltage amplifier and a current buffer working together. In one of my previous videos, I have explained a very simple audio amplifier which utilizes 2 transistors along with other basic components like resistors, capacitors, microphone, speaker, and other stuff to make a simple megaphone. All details including coupling capacitors, biasing resistors, microphone circuit and other things are explained in detail. There is a link to that video in description. So guys, this video is ending, but there are a lot of other applications of transistors which are not covered here in this video. Applications like logic gates, voltage level shifters, active filters, edge bridges, oscillators, resistor simulators, and much more other simple and complicated applications. If you need to learn more about other applications of transistors, please let me know in comment section below. So guys, I hope you enjoyed this video and learned something new. Thanks for watching. If you enjoyed this video, please hit the thumbs up button, and if you like this video, make sure to subscribe for more.